So we looked at a few examples of the kinds of shapes that a quadratic equation in 3 variables can produce in 3D space. Right? We saw this cup shape. I didn't name this. This is called a parabolic ellipsoid, I think. The name isn't important. We got this weird shape, which is kind of circles in one direction and a hyperbola in the other direction. This is called a hyperboloid of one sheet because it's one piece. There are a few other kinds of shapes that you can get. So let's just have a look at those. You don't need to memorize these. So again, the point of looking at these surfaces is just to see what can happen, so that if you want to get some idea of what, and if you have some quadratic equation and you want to have some idea of what it looks like, looking at cross-sections can tell you, but if you know what the possibilities are, you don't have to look at as many cross-sections. Okay, so it's just good to know what the possibilities are. So you don't need to memorize these names or the types, the particular forms of equations that produce particular shapes, but just be aware of what the types of shapes are. All right, so there's an ellipsoid, right? This is, all the cross-sections are ellipses. Because the reason that they're all ellipses is because there are all pluses here. Again, you don't need to memorize the form of this equation or anything, but all the cross-sections are ellipses. Another example that we already have seen, another type of quadratic surface that we've already seen an example of, is this kind of shape. So we call this a hyperboloid of one sheet. So it turns out that because there are intercepts in 2 directions but not the third direction, it looks like a hyperbola where 2 of them have a plus and 1 of them has a minus. The cross sections in one direction are ellipses, and in the other direction, in 2 other directions, they're hyperbolas. So this direction is a hyperbola, and this direction is also hyperbolic cross sections. Okay. So here we had 2 terms with a plus and 1 term with a minus. If you have 2 terms with a minus and 1 term with a plus, well, you're going to get hyperbolas again, except there are 2 directions with no intercepts and 1 direction with intercepts. So still you have hyperbolic cross sections, like this cross section here. Right, there's a hyperbolic cross section. But it can't sort of meet in the middle because two directions, the x and the y direction in this case, don't have intercepts. So this splits our hyperbola up into 2 separate pieces. Varying these numbers a, c, and b, and also in the hyperboloid of one sheet, it just sort of changes what the elliptical cross sections look like. Right? So for a hyperboloid of 2 sheets, where we have these 2 separate pieces, we still have hyperbolic cross sections, right? For both of these hyperboloids, it's as if we took a It's as if we took a hyperbola and rotated it, but the difference is which direction we rotate it, right? So for the hyperboloid of 2 sheets, I guess I should draw that one down here. For the hyperboloid of 2 sheets, we're rotating it around the axis that does touch the hyperboloid, right? So each of these separate pieces of the hyperboloid sort of stay separate and form their own kind of cup shape. But for a hyperboloid of 1 sheet, we're rotating around an axis that doesn't intersect the hyperbola, and when we do that, the rotation sort of joins the 2 pieces up, and you get this single sheet hyperboloid. All right. So other examples of shapes that you can get, an elliptic cone. So if you look at the hyperboloid equations, there's a non-zero constant on the right-hand side. Well, if you make that constant 0, it kind of draws the middle of the hyperbola all the way to the origin, and it makes a cone instead. Okay. The reason that this makes a cone is, if we look at the simplest example of an elliptic cone, where it's x squared plus y squared minus z squared equals 0, if we move the z squared to the other side, x squared plus y squared equals z squared, and then take square roots on both sides, we get plus or minus sorry, plus or minus, there we go, square root of x squared plus y squared equals z. But x squared plus y squared, that's sort of distance from, that's distance from the z-axis. So we might write that plus or minus r equals z. So this looks like the height is the same as distance from the origin. And yeah, that's what's happening here, right? The height above the xy plane is the same as the distance from the z-axis. So that's why we're getting a cone. And of course the origin is included because the height there is 0 and the distance from the z-axis there is also 0. So that's why we get a cone in this case. Yeah, fair enough. Notice the cross sections are going to be the cross sections in the direction with the two pluses are the cross sections that turn out to be hyperbolas. Oh, I should have mentioned this for the hyperboloids as well. Where the minus signs appear. So on this one we only had one minus sign. On the hyperboloid of 2 sheets we had 2 minus signs. Where those minus signs show up determine which direction this hyperboloid goes, right? So here we had a the minus on the z-axis, which is why this one goes up. If we had the minus sign on the x term instead, it would open sideways like I've drawn over here. So the minus sign just tells you which direction it goes. But notice that if you just keep your eye on which two, well, let me clean this up. If you just keep your eye on which terms have the pluses, the terms that have the same sign, so either plus and plus or minus and minus, that's the direction where you get elliptical cross sections. So if you know which way have the elliptical cross sections, it's straightforward to piece together which way the hyperboloid is going. And same thing for the cone. All right, another possibility is an elliptic hyperboloid, which looks like this. Elliptic paraboloid, not hyperboloid. An elliptic paraboloid, if you look at, if z is constant, then this looks like the equation of an ellipse, so that's why we have elliptical cross sections going in one direction. But in the other direction, right, if we say hold y to be 0, so this is gone, then we have z equals x squared over some number, and so that's a parabola. So that's why we are getting parabolic cross sections going the other way, and of course this way as well. Right. So an elliptic paraboloid, we did see an example of this. This is one of those parabola-shaped cups. The final example is a hyperbolic paraboloid. So this one's a little tricky. If z is a constant, then this looks, whoa, crazy. OneNote sometimes converts certain shapes into, certain pen-drawn shapes into geometric shapes that it thinks you're trying to draw, and that's what it did, and that's not what I was expecting. Anyway, so if z is a constant, this equation is a hyperbola. So the horizontal cross-sections of this shape are all hyperbolas. Right? Up here, there's one part of the hyperbola and there's another part of the same cross-section. So horizontal cross-sections here are hyperbolas that open sideways. Cross-sections down lower, right, if we look at, say, the very bottom cross-section, there's part of a hyperbola and there's another part of the hyperbola. So that's a hyperbola that opens this way. Right. So that's a hyperbola that opens in the opposite direction from the higher hyperbolas. And right in the middle, there is a spot where there are two straight lines that intersect. Right? And those two straight lines, right, as those two straight lines are sort of the intermediate case between hyperbolas opening one way and hyperbolas opening the other way. Right? As we get closer to the middle, the cross section, the hyperbolas that are the cross section sort of tuck closer and closer into the origin, and then right in the middle they cross like this, and then they sort of separate and become hyperbolas that open the other way. Okay, so that's the horizontal cross sections for this. The vertical cross sections, well, if y is 0, then we're left with z equals x squared over a squared. So that's going to be parabolas. So all of these vertical cross sections are parabolas. So for example, here's one, here's on the back side, here's another, right? And it's, for this particular picture, it's hard to draw, but the cross sections going, actually no, it's not hard to draw. Here's a parabola going left and right, and then on the back side there's another one back here. So these are all of the interesting cases that we get for graphs coming from quadratic surfaces that come from quadratic equations. Of course, another way we can get a quadratic equation is just by having all of the square terms disappear, but then we get a plane and not a new surface. So again, let me emphasize that I don't expect you to memorize like each form of the different shapes here. All right, all I want you to be aware of is what types of surfaces can show up, so that if you have an equation, you can slice it only a few ways to figure out what kind of surface it is.